Hi, I'd like to talk to you about a phantom that we've been developing at Royal Brisbane, mainly to do with some cardiac amyloid phantoms. So most phantoms in nuclear medicine are either 100% displacement, as in the JZAC phantom, you have a solid block inside a uniform background, or they're a replacement phantom. So you've got some background activity and you replace it with activity inside a volume, and all volumes have walls. So you have a discontinuity between the background material and the activity. One of the slight deviations, this is the Hoffman brain phantom, which uses 19 plates with different partial inserts to give you a 4:1 ratio of grey on white matter instead of an in-between displacement or replacement phantom. I was wishing to examine this sort of role a little bit more. As I said, we have a cardiac amyloid phantom. We're looking to do some work at qualifying some sites for a multi-center study. We want to investigate the cardiac environment as well as the general spec quantitation. Are the different cameras at different sites producing quantitative spec the way you expect? So we've chosen to look at a biodex anthropomorphic spec phantom with a cardiac insert. It's got a liver, lungs, a fillable spine, a cardiac insert. The liver insert always has some space where you can actually put extra chambers. I'm going to put 2 extra chambers inside that, so we've got quite a reasonable level of several quantitations. The cardiac chamber comes with several displacement solids or fillable sections, but these are quite small, and I was wanting to look at something a little bit more different. Previously, we've been doing some 3D printing, and a lot of 3D printing software effectively provides you with an infill parameter that provides a support for external layers. If you like, it's a little bit like trabecular bone inside cortical shell. And if you choose the infill in a pattern that is continuous all the way through, it looks a lot like a fillable chamber. So I was wishing to look at this in a nuclear medicine displacement phantom. So I printed planned out some 2 centimeter cubes with 0 skin thickness, and then set them between 0 and 100% fill in 10% intervals. I then immersed them in a 2 centimeter bath, so it's the same level of technetium resting on a collimator on the bath. This is the phantom, so this is 0% fill. This is 100% fill, likewise stepping back again. And the water level was exactly on the top, so the meniscus is just touching. And this is the sort of image you get. 0 counts, 100% fill, and 10% fill, or 90% counts, and this is 100% counts. I was looking at as a contrast phantom, which there's 3 separate rows. I then put some regions of interest on that, plotted them out. This is obviously 100% displacement or 0 counts, and this is 0% infill or 100% of the counts. This should be 100% of this value. Unfortunately, it's not linear, and if you plot out the results, it starts off quite reasonably and then it wanders off a little bit, and 0 displacement is obviously not 0. There could be a bit of water underneath this section. So background corrected it, and even background correcting it, the triangles, it doesn't quite come in. So a nice simple solution potentially offered by the printing software was going to work. So it's not linear, and some of the small holes that you use in the very fine fill were hard to get the water through, even with a surfactant. In this case, just simple dishwashing detergent. Okay, so I started thinking about a more manual method of filling the space. So I considered the repeating block of dimension O and I internally. And then obviously we're looking for a whole area in proportion, the percent proportion of the repeating area. So it's a pretty simple, straightforward relationship. So you can wind up with an O dimension, which is the X percentage times the square root of I. And this allows you to set I, your internal channel, which needs to be big enough to get water through. Too small, it's hard to fill, and allows you to calculate an O. How do you then go about doing that? So we set up the same sort of thing in the planning system, or in this case, a program called Tinkercad, a 2 centimeter by 2 centimeter block, and set out my hole sizes at 4.3 millimeters at a 5 centimeter displacement, and just repeated them until we had a grid. Overlaid the grid, fused the 2 objects, and there you are. That gets sent to the printing steps software, which then prints it out. 15 minutes, it's not very long. And then that was the process about developing the fillable phantom. To make sure the fill was doing what it was meant to do, I printed out a 2 centimeter block with 100% fill, measured its external dimensions and its weight with calipers, so that's 100% fill. And then using the percent fill I was expecting and calculated the densities, we then iterated for O and I to make sure that we were accommodating for some printing errors. The printers tend to over extrude the holes and fill them in a little bit and make that otherwise a bit off what you're requiring. So we wound up with, for 75% fill, we've had 2 millimeter holes repeating every 4 millimeters, 50% fill, 1.75 mils, holes and repeat every 2.4. And for 25%, it's about 4.3 millimeters holes and repeating every 5 millimeters. So this is the sort of structure. By density, that turned out to be 77% basically, 50% and 26%. So for my purposes on this particular event, that was enough. Printed that phantom out and then again immersed it to see what would happen when you scanned it. The water level had the same depth, so you're getting 100% displacement and 0. These are our regions of interest, and if you look at the activity for each of those, this will be the inverse of the activity, obviously. This is 24%, 52%, 75%. Again, for my purposes, that's close enough. Let's move on to 3 dimensions. This really isn't anything more than a step wedge can't do, and in 2 dimensions, it's pretty boring, but 3 dimensions, it's a bit more interesting. So we took our cardiac insert, measured the myocardium chamber, and generated a model for a wall with infills. So it's effectively a circle, put a hole in it, chop out a quarter because I wanted a quarter to be 100%, and then put in the regions of 25, 50, and 75% fills, created the object, printed it, and inserted it in the chamber. And this is the myocardium chamber inside, and this is the, if you like, the ventricle inside with 0 activity, and the activity was sitting in here. With care, you can do this with very few bubbles, and if you want to make sure that you haven't got bubbles in the apex, you scan it prone with all the bubbles sitting up in the base plane. This is what the phantom looks like. Lungs, fillable spine. In the liver, I had 2 other regions, and this is how you fill the phantom. It's a bit of a fiddle to fill it. You have to take the lid off it, fill this, then reassemble it. Materials, we use an Ultimaker 3 printer. That's the print area. It's a fused filament fabrication, effectively a glue gun on steroids. The filament is polylactic acid, and the specific gravity is about 1.24, and the attenuation value of about 90 pounds per unit. So it's a bit dense than ordinary tissue, but nowhere too extreme. This is the sort of imaging you get: the spine phantom, one of my objects in the liver phantom, and the activity in the heart. There was, on this particular scan, a couple of little air bubbles, and you can see the mesh patterns appearing in the CT, but certainly in the nuclear medicine resolution, you cannot see that at all. And as I slice through the object, this is what we're seeing. This is the apex that's not filled. Reorienting that to the cardiac axis, we use some software called Karamas. This is what I use as my 100%, the apex, which is unfilled. We then set regions across each of the different chambers, and then compared those regions. And this is effectively the 4 sets of 25, 50%, 100% in the myocardium, and the 100% as what I was using for myocardium for a normal fill, sorry, 0 fill. So the results, as again, we were looking for a 75% fill, or a density of 76%, or if you will, the space of 25%, which should have given us 25% of the counts. So 23, 24, and the spec gave us 32, a little off, but not too bad. The 50% region for the density gave us 50%, pretty much on the dot. The planar activity was 52%, and the spec activity was 47%. And for a 75% value, we had about 73% by density, 75% by planar activity, and 82%. So plotting those out, that's the sort of, this is the spec data, the red squares. So again, for a relatively small region and a relatively initial approach, I thought this was quite worthwhile. Now, as far as how this phantom goes when it gets sent out across the other sites, that's a talk for next year. The other thing that we're thinking about now is what else can we do with this sort of process. So the IEC phantom is a nuisance to fill. It's very fragile. We've broken one. It's time consuming to fill. I'm wondering if we can't just print out an object with channels in it and a great big void in the middle and just drop it into a uniform fill phantom. Thank you very much for your attention.